Question? Okay. Let's do an example. So which problems we had that we calculated the electric field? We had already discussed the electric field of a point charge, and we also calculated the flux going through a sphere. And we had also studied the electric field of a linear line charge. Let's say this is lambda, the charge density, and it's also part of your homework. And we had obtained that the magnitude of the electric field was lambda over 2 pi epsilon 0 r. Do you remember? And it was also pointing away from the wire. So at this point, it is moving in this direction. If lambda is positive, this is the electric field. At this point, it is in this direction. If you are on this ring, at this point, it's in this direction, etc. It's always pointing away from the wire. And it's horizontal. If you assume the wire to be vertical, it's always horizontal, and this was the magnitude. Now let's take this wire, and let's imagine a cylinder around the wire. Not a full cylinder, let's say a partial cylinder. Of radius r, and let's assume the height is h. So what is the electric flux in this case? Let's calculate this electric flux starting from the electric field. Now you see the definition of the flux is just E dot dA at every point. So this is not a flat area, so we have to imagine that we divide it into very, very small pieces, and each one of that very small piece would be almost flat, and for an almost flat area, we can talk about this dA vector. If we know the electric field at that point, we can take the scalar product and sum over all those small parts. And that is what we will do. Of course, first of all, we have to decide on the direction of this dA. This is not a closed surface, so which direction should we choose? Out. So you are saying this is the out direction, right? Why not? Who tells you that this side is the inside? There is nothing that tells you that that is inside. So you are absolutely free to choose whichever direction you want. And I will choose that one.
But you can also choose inside.
Sure. That's up to you. I mean, it's just like, if you remember your mechanics courses, we were free to choose the x direction in this direction or the other direction. It was up to us to choose it. The same idea over here. The area, you can choose whichever direction you want.
So why not let innovation help us instead of go against us?
Well, I'm a mean teacher. I want to confuse you. Other questions? Well, the next lecture I will be bringing my big stick, so that makes a louder noise. That's more effective than starting lecturing right away. Yes?
About this line, why it's somehow radially spread outside, rather than we know that the point of charge is on all sides.
Okay.
Distribution. Why is that?
Well, okay. For the time being, I will just give let's say, I will be escaping your question. I will just say that that's what we calculated. I will give a more detailed answer later on. Don't forget your answer. That will be an important thing. We will be discussing a bit about the symmetries. That will be a crucial point in using the Gauss law also. Later on. Okay? Ask me again, though. So we had already calculated the electric field was horizontal. It only depends on the distance from my wire. It doesn't depend on the angle. And remember, the electric field is proportional to the density of the electric field lines. So the density of the electric field lines have to be uniform as long as we are at the same distance, because the magnitude doesn't change. Now let's just assume this, take this area over here. I have this very small area. The area vector is pointing in this direction. This is my dA. The electric field is pointing right the other direction. These are they are perpendicular. If you just elongate this line, it's perpendicular to the wire. So E dot dA would be the magnitude of the electric field times the magnitude of the area element times cosine of, well, the angle between the two is, one is in this is the dA, this is the E. No, this is dA, this is E. So the angle between the two is 180 degrees or pi radians. This is equal to minus, the magnitude of the electric field is lambda over 2 pi epsilon 0 times capital R, because I said that this cylinder is at a distance capital R, times dA. This minus sign, the cosine pi is minus 1. So this is my E dot dA. Now, to calculate the flux, I have to sum over all these elements. Remember, whenever you see an integral, that's just a sum. So this is equal to the sum of minus lambda over 2 pi epsilon R dA minus lambda over 2 pi epsilon 0 R sum over dA. Well, this is one patch. This is the area of that patch. I'm just summing over all such patches, but that would just give me the total area of my hemicylinder. And the total area of my hemicylinder, 2 pi epsilon 0, the area is just pi r squared over 2 times h. Do you agree? No, I also don't agree. It's pi r times h. Pi r is this circumference over here. This is a half circle. The circumference is the full circumference is 2 pi r. I have half of it is pi r times the height of the cylinder. That gives me the side area. So the electric flux,
I think you've got an R. You made minus lambda.
so let's see, these pi r's, they cancel. So the total flux turns out to be minus lambda h over epsilon 0 times 1 over 2. This is the total flux passing through this cylinder, half cylinder. Yes?
The circumference of a circle is 2 pi.
Well, this is not a full cylinder, it's a half cylinder. So I just take the half of the circumference. Let's just do the full one. This is R, this is H. Let's just choose the direction to be this direction this time. just to be meaner. So let's see what will change in our previous derivation. If instead of this half cylinder, we take the full cylinder. Here I chose the area element to be pointing in the opposite direction. So this is the E, this is the A. The angle between the two would be 0. So there is no minus sign. That is one thing that would change in my result. The second thing will be the sum of this dA. Now I have the full circumference. Instead of the pi r h, I would get 2 pi r h. So I can just write down the result. Lambda h over epsilon 0. Now what is this lambda h? So you see, this is my cylinder. So this length is h, sorry. That is the length of the wire. This one is the length of the wire, which is inside my cylinder. Lambda is the charge per length. If the length is h, the total charge of this segment is lambda h. So this lambda h, so E dot dA is equal to the charge inside divided by epsilon 0. I didn't forget this circle over here, because this is the surface I consider over here is not a closed surface. I'm not considering a closed surface, so it's not an area integral over a closed surface. So that's why I don't put that circle sign. Now let's take a closed cylinder. I still have the wire. I assume a closed cylinder, radius r, height h. This time all of these are closed. Now I want to calculate E dot ds, E dot dA. We have this integral. We have to divide our surface into small patches, and we have to sum them up, all these patches. I can group them and sum them separately and then take the total sum if I want. So this integral, I can say that this is E dot dA integrated over summed over the patches that are on the top of the cylinder plus E dot dA. This is again a sum of area patches, but this time I only consider the patches at the bottom of the cylinder, plus E dot dA from the sides of the cylinder. Now the side. Remember, this integral, you just imagine that you are dividing this total closed surface by very small patches. I just sum the patches on the top, that gives me this integral. I just sum the patches on the bottom, that gives me this integral. And then I just sum the patches over the sides, that gives me this integral. What are these? Why? You see, at the top, this is my dA. At the same point, this is my electric field. The angle between dA and the electric field is 90 degrees. So this is 0. At the bottom, at this point, this is my dA, and this is my electric field. And the angle between the two is 90 degrees. Again, from the bottom E dot dA. This term is 0 for each one of the patches making the full bottom area. So this is 0. The only one left is this one, and that is what we had already calculated. So this is 0, this is 0, this is we had already obtained that it is lambda h over epsilon 0. And this is just a verification of Gauss' law. E dot dA is equal to the total enclosed charge over epsilon 0. Again for this case. Now, any questions on this one? Now, in these examples, we mainly started from the known electric field. We chose a surface, and we calculated the flux over that surface, like in this one, it's the closed surface, and then we verified the Gauss law. Now, we can go the other way around also. So we can just, knowing the Gauss law, we can derive the electric field. And that is what we will do next. But if you have any questions. This one. 180 degrees or pi radians. You see, in this one, this is the dA vector, this is the E vector, the wire is over there.
Instead of a circular-based object, could we use something like a square or a rectangle?
We have a point charge. And let's imagine we have a cubical surface. The charge is on the center. This is L, this is L, this is L. This is a cube. And we want to find the flux on each side. Would you be happy with this example? You see, the problem over here, what you should do is the same, basically. You divide, let's say, this side to very small air patches. We know what the electric field is at each one of the patches because we know the position of each. In principle, we know the position of each one of these patches. The electric field of a point charge will be radial. In this direction, this is the electric field. Now the dA vector will be just perpendicular to that side. And this angle over here, let's call it theta. The problem is, if you change your patch, this theta will change. It is doable. It will be lots of mathematics, lots of integration. In principle, you can do it. Well, in this particular case, there's a short trick. Because we know E dot dA over all the sides is the flux, the sum of the flux going through the sides. But since the charge is at the center and all the sides are equivalent to each other, this is 6 times phi side, the flux through one side. At the same time, this is Q over epsilon 0. Yeah, it's a cube. We just place the charge at the center, etc. I mean, physically, I don't think you will ever face to calculate such a thing, flux, but it's also possible. I mean, what you should actually do, it will be a highly computationally intensive task.
Okay, we'll have to change theta, etc.
Yeah. The same thing will happen for the cylinder. If you don't assume such a circular cylinder, it will be quite hard to calculate it. Unless there's some other symmetry, like in this one, all the sides contribute the same. Now let's calculate the yes. Okay, this is my surface, right? Half cylinder. The wire is here. Now in this shape, it looks something like this. The wire is passing through here. I am looking at this point over here. The electric field will be in this direction. Now dA, I have two choices. I can choose the dA, it should be perpendicular to the surface. It can be either in the same direction as the electric field, or it can be in the opposite direction. I have a choice. You have a choice. It's just a choice. And I prefer to choose it towards the wire. Why? For no reason, except I'm trying to confuse you. I have one more question, though. Now let's look at this one. If you have realized, but in passing to this example, I changed the direction of the area. Rather than pointing towards the wire, in this closed surface area, I chose it to be pointing away from the wire. But if it's a choice that I'm free to make, I could have just kept it in the same direction as pointing towards the wire. But if I change the direction of dA, I'm basically multiplying everything by a minus sign. So I would get this integral will be minus lambda h over epsilon 0, not plus lambda h. Now, the thing is, what is this Q enclosed? Q enclosed is the charge on the inside my surface. And the inside we define as our vector, the surface area vector, is pointing from inside to outside. So if I change the direction of A, I'm basically changing what I call as inside and what I call as outside. Now when I change my area vector to be pointing towards the wire is now outside. Inside is all this region. The rest of the universe is my inside. If the universe is neutral, and I know that lambda h charge is outside my surface, then what remains inside will be minus lambda h. So this result is still consistent. But as your friends had complained, intuitively you would anyway choose the dA element to be pointing in this direction, so the inside charges, the enclosed charge will be obvious. Now let's look at the electric field of a point charge. Now we already know what the electric field of a point charge is, but the idea is how can we obtain that using the Gauss law? Why? Intuitively, yeah. So let's say we have this plus Q charge somewhere in space. And we want to use the Gauss law to determine the electric field everywhere. And this is our law. A dot dA is equal to Q enclosed divided by epsilon 0. Well, there will be two steps in using the Gauss law, which most of the time you ignore the first one. The first one is you have to first study what the electric field should look like. so that you should be able to choose a Gauss surface. And your friend said, a sphere. But why a sphere? What makes a sphere so special that we can use it? How do you know?
If you put the cubes on,
How do you know?
because the electric field lines are going away from it.
How do you see, the idea here is that we will start by assuming that we don't know the electric field lines of a point charge. That we don't know. We don't know the expression. So we have to first argue that the electric field lines should have certain properties. How can we claim, without knowing the electric field of a point charge, how can we complain that it's radially out?
We could say that at all points it has to, there is an electric field, we know that, right? And,
There is some electric field that we know. Or, I mean, we might see from the Gauss law that there might not be an electric field. We don't know.
there might not be an electric field.
Well, we have to say whether there is or none. It's zero or none, Gauss law will tell us.
We're working on the assumption that there is an electric field, right? You just asked us to tell us the shape. So we could say that the shape has to be radially outward because practically we know that as the distance increases, the effect of that charged particle decreases, right?
We don't know that yet.
Not even practically.
No.
And we don't know what's the Coulomb's law?
We don't know the Coulomb's law. We only know the Gauss law. And we know that the universe has certain symmetries. I mean, if you look at it like this or turn around like this, I mean, at least for a point charge, nothing changes. It should also be true for the electric, anything created by this point charge. So that's basically the idea. So what we will do is, okay, this is the point charge. You can imagine that you just lie down so that you change your own orientation, or you look at that point charge from here, or you go to the other side, look at the point charge from there. Will you notice any difference? If there's only the point charge in you, there won't be any difference in the charge. So there shouldn't be any difference in the electric field created by the charge. So if you look at it from here, you lean down, look at it from the bottom or from the top, you should see exactly the same thing. So the electric field should also have the same property. So what are the possibilities for the electric field lines?
Wait, why? You just said because we can see it the same from all angles, then the electric field should also have the same properties. Why?
We don't know what the electric field is. We don't know.
We don't know the electric field. But what do I know? I mean, the nature should be independent of how I look at things. If I look at it from here, or if you look at it from there, or if you look at it from the top, from the other side, the nature doesn't care. The natural laws do not care. Of course, the charge distribution might look different from different points, but if you have a point charge, the charge distribution also looks the same. You cannot even tell whether you are looking at it from this side, from the other side, or from there if you are not looking at something else. And assuming there is nothing else except that point charge, it should look identical in every orientation. So the electric field lines should also have exactly the same property. Now, there is only one configuration which satisfies this property, that the electric field line should be radially outward. Not exactly. There's one more subtle point. If you put a mirror over here, it should also look the same. So that kind of tells you that there's only one possibility. The electric field lines have to be radial.
Could you repeat the mirror point? Like you just said if there was a mirror.
If you put a mirror over here, it should look the same. Now, my issue was this one. What about such electric field lines? And to eliminate such a possibility, I just said that even with a mirror, it should look the same. Not as mean as I am. Yes?
But when we are talking about numbers where we are going to about light. So it's the what radiant is light? Isn't the force light?
Light, you mean?
Light is radiant, I think.
I mean, eventually we will connect it to the light, but I mean, we don't have the light. Here we only have the electrostatics. So there's no radiation, there's no photons, there's no light. The only electric field lines, or electric field. So it should be radial. Now, this tells me that, okay, one thing, the electric field should be in the radial direction. Secondly, the magnitude of the electric field can only depend on the distance from my charge. It cannot depend on anything else. It cannot depend on the orientation relative to my point charge, because I cannot really talk about the orientation. I cannot measure it without some other reference point, which doesn't exist. I don't know whether the magnitude is decreasing with R or not. I don't know yet. The only thing I know, just looking at the charge distribution, so-called looking at the symmetry of the charge distribution, I know that the electric field should be radial, and the magnitude should only depend on the radial distance. Now, if you want to evaluate an integral, you should know what you are integrating, right? That is one case if you want to evaluate an integral. Another alternative is whatever you don't know should be constant, so you can take it out of the integral. I mean, if there is some constant inside the integral that you do not know, you can just take it out and evaluate the integral. That's kind of easy to evaluate. Now, the point is, what keeps the electric field? On which surface the electric field has the same magnitude? Since the magnitude depends only on R, if you choose a surface for which R is constant, the magnitude is constant. So that is why for a point charge, we use a spherical Gauss surface. Now, without first claiming this thing, you cannot choose a spherical Gauss surface. You don't know which surface to choose, basically. Because for a rectangular surface, for a rectangular prism, electric field will change from point to point on my surface. E dot dA will change from point to point on my surface. So the function I do not know, so I cannot evaluate the integral. I cannot make use of it. It will still be valid. The Gauss law is valid for whichever surface you can imagine. It's valid for this spherical surface. It's valid for a cubic prism. It's valid for any closed surface that you can imagine. But for an arbitrary surface, it won't serve any purpose for you. So to be able to obtain the electric field of a point charge, in this case, we need a spherical Gauss surface. Now, for a spherical Gauss surface, dA, the area element, is also in the radial direction. I can just take it to be outside, pointing away from the point charge. So this is my Gauss surface now. Let's say at a distance R. I can imagine small patches. Whichever patch I imagine, this dA will be also in the radial direction. Now I can evaluate E dot dA. It's the magnitude of the electric field, which we know it depends only on the radial distance. And on the surface, the radial distance is fixed to be capital R. Times the magnitude of the area vector. Well, the angle between the two is 0. Now I can evaluate this integral, although I don't know what the electric field magnitude is. I don't know what this one is, but on the chosen surface, this is just a constant, so I can take it out of the integral. Over this closed surface, E of R, I can just take it out. And the sum of the areas just gives me 4 pi r squared. And the total charge inside my closed surface is just q over epsilon 0. So we have the magnitude of the electric field is 1 over 4 pi epsilon 0, q over r squared. Now, some of you were asking, why do we have the electric force has this 1 over r squared behavior just like the gravity? Now I have a different answer for you. Because both gravity and the electric field, they satisfy the Gauss law. And this 4 pi r squared is nothing but the total area of the sphere, the surface area of the sphere in 3 dimensions. If we were living in, I don't know, 5 dimensions, it will have a different dependence.
So how come we didn't learn Gaussian sphere when we were learning about gravitational force?
Well, for gravity, we cannot really do much. We cannot talk about conductors, insulators, so it doesn't really, it satisfies the Gauss law, but it's,
No point.
there's not much point, at this level at least.
At this level.
One day, if you study general relativity, for example, there you first derive the Gauss law for gravitational field.
Okay, is it because that's when we use gravity as a field instead of a force?
Yeah.
Okay.
So these are the basic steps if you want to use the Gauss law. Tomorrow we will continue studying the Gauss law. We will be discussing in more detail. But don't forget the first step. How do you choose a surface to use the Gauss law? I mean, in high school, most of you are probably familiar with the Gauss law. We still have time for a quiz. Now, you have learned in high school that, okay, for a point charge, you use a sphere. For a plane charge, you use a rectangle, etc. But why? You should first, it's more important to understand why do we choose a spherical surface? It is mainly because just looking at the charge distribution and how it looks from different points, we know that it doesn't change. The charge distribution doesn't change. So the electric field should not change depending on at which point you look at it. So in that case, the electric field has to be radial. There is no alternative to it. And we also know that the magnitude can depend only on the distance from the point charge. This information tells you to choose the surface, the spherical surface, because for a spherical surface, the magnitude is just constant. And since it is constant, we could take it out of this integral and evaluate the function, although we don't know what the electric field is. Okay, any questions?
Why didn't we do the same for the line charge?
We will, tomorrow. It will be our next example. How do you calculate in your homework, you are already evaluating these integrals. Once you understand the Gauss law, there are only very few cases in which you can actually use the Gauss law for practical purposes, like in this one. But you can just derive it in a couple of lines instead of just pages and pages of integrations. Any questions?
What is epsilon?
It's called the permittivity of space. It permits the electric field to move in this space. We will see that when space just behaves like an ordinary matter in a sense.
Is it different for different materials?
Yes. The effect of different materials, for most of the materials at least, is basically to modify this constant.
Do we have the same for gravity?
This permittivity constant. I think the Newton's constant would play that role. But the gravity doesn't change from medium to medium. Yeah. Well, I mean, the problem with gravity, the difference with gravity is that in electromagnetic case, we have both positive and negative charges. We have attraction and repulsion. In gravity, we don't have repulsion. We only have attraction. So one of the reasons why in materials, the electric field, this epsilon changes, is that the positive and negative charges, they just move differently. Negative charges tend to cancel the electric field at certain regions. Positive charges tend to enhance it, etc. So that is why epsilon 0 is modified. We don't have the analog in gravity.
Is it possible to create a uniform gravity field?
Well, if you can manage to create in empty space planar mass, uniform mass distribution, then you will be creating a uniform gravitational field. Or another alternative is, in this classroom, the gravitational field is more or less uniform. I mean, you won't be able to measure the difference from this point to that point. It's uniform in this classroom.
So for a big enough surface, big enough sphere on the surface.
For a small, you see, if you are talking about a surface, you cannot say a surface is big or small. It has a dimensionful parameter. You have to compare surfaces. The surface in this classroom compared to the total surface of Earth is very small, so it's almost flat. Okay, see you tomorrow.